In this section, we're going to introduce planes in R3, planes in three-dimensional space. Before we jump right in, though, I want to talk about lines in R2, lines in two-dimensional space. This will give us a nice parallel to work with when we move to planes in three-dimensional space. So in the previous section, we learned about how we could express lines generally in any number of dimensions using vector equations. But I want to go back to the old style lines and equations of lines that we knew for two-dimensional space. So for most people, when I ask you to write the equation of a line, you might think y equals mx plus b. And that's great, but actually not all lines can be described this way. In particular, vertical lines cannot be described using this equation because vertical lines would have an infinite slope. But there is a way that we can describe any kind of line. The equation ax plus by equals c is the equation of a line in standard form, and any line in two-dimensional space can be described using this equation. So this line cannot be used to describe vertical lines. And this one can be used to describe any line in two-dimensional space. And so this second equation here, it's going to be the equation that we focus more on. Okay, and just to be clear, a, b, and c are constant values. X and y are variables, right? So let's kind of pull this over so we could think about this a little more deeply. Now that we have a background in vectors, we can actually rewrite this using vector notation. In particular, the left-hand side here, we have a constant times one of our variables plus a constant times another one of our variables. That looks a lot like a dot product, doesn't it? In particular, the dot product of the coefficients with the vector of variables. Okay, so one way of looking at the equation of a line like this is as the equation telling us something about the angle between the points on the line and this particular vector. Okay, so I want to get at the heart of what that relationship is. So I want to look at a simple case first where c is 0. So let's consider the special case where c equals 0. So in that special case, we have ax plus by equals 0. And thinking about that left-hand side of the equation as a dot product, we have the coefficients ab dotted with the vector of variables xy equals 0. And hopefully, when I write this, alarm bells are starting to ring in your mind because you were like, wait a second, a dot product that equals 0, that means these two vectors must be orthogonal. So what does that mean? Well, notice first that the origin is a point that's on the line. Okay? And you can see that if x and y are both 0, clearly it's a solution to the equation, whatever the values of a and b are. So let's say this is the line. Okay? And here, every vector xy, if it's a point on the line, then the vector from the origin to the point, the vector xy, is parallel to the line, right? Now, the claim here, the observation here, is that when we have 0 on this side, vector AB is going to be orthogonal to vector xy, which means it's going to be orthogonal to the line. Okay? When we have a vector that is orthogonal to a curve or a surface, we give it a special name. We say that the vector is normal to the curve or normal to the surface. So in this case, vector AB is normal to the line. Okay, it is the normal vector of the line. Do be careful here. We use a lot of words that kind of sound similar. Norm, normalize, normal, they all mean different things. Here, the normal, a vector normal, is a vector that is orthogonal to the curve or the surface. Okay? And just so you're convinced, let's see a concrete example here. So let's graph the line. And it's normal. So let's do 2x plus 3y equals 0. So there are lots of ways to graph a line. I could put it in y equals mx plus b form, rearrange it. But as long as I can find 2 points on the line, 2 points determine a line. So if I could find 2 points, the line through those 2 points is the line I want. So I do see that the origin is one solution here. Okay, 0, 0. Another solution to this equation, another point on the line, would be negative 3, 2. And so with those 2 points, we have the equation of a line right there. So that's the line. Now let's graph its normal. So its normal, thinking about this as a dot product, we get vector 2, 3 dotted with xy equals 0. Its normal would be vector 2, 3. Okay, so 0.23 is right there. And if I draw the vector in standard position, I could see that the normal vector 2, 3 is orthogonal to the equation of a line. Okay? All right. So that's the special case where we have 0 on one side of the equation, where c is equal to 0. But in all those cases, the line goes through the origin. What if the line doesn't go through the origin? What if it goes through some other point? Okay. So let's find the equation of a line. Passing through the point. X naught, y naught. And with normal vector, AB. Okay, so here it's very similar to what we've been doing, but now the line is passing through a point that is not necessarily the origin. Okay, so let's think about this. So say x naught, y naught is maybe here. Okay, and maybe vector AB points this way here. Maybe that's our normal vector, which means our line would be like this. Okay, so how do we find the equation for that line? Well, just as before, every vector parallel to the line, would be orthogonal to vector AB. Okay, so let's take a point here. This point is maybe xy. Okay, if I want this, sorry, not vector xy, point xy. Actually, maybe I should do it in a different color just to distinguish it a little bit. So say this vector parallel to the line is pointing to point xy from the point x naught, y naught. Okay, then this vector here, end minus start, I want to end up at the point xy. I want to start at the point x naught, y naught. Okay, see how that works? This vector that's parallel to the line, to get that vector, I take where it ends up minus where it starts. End minus start. And so, this vector, together with the normal vector, are going to be orthogonal. So I'm going to use the same kind of logic, get my normal vector, dotted with the vector parallel to the line, the one that points to some point on the line xy. If I take the dot product of these two vectors, I still get 0. So now this is the general equation of a line in 2 dimensions written in vector form. Let's do the vector arithmetic and see what we get. Okay. So first you would subtract the 2 vectors. Leaving me a vector x minus x naught as the first component, y minus y naught as the second component, equals 0. And if I take the dot product and multiply corresponding components, and I have the equation of the general equation of a line in 2 dimensions. This line can go through any point. Okay, and I could actually go even further. This is a nice form for the equation of a line, but I could actually go even further. Let's go ahead and distribute. If I do that, I get ax minus ax naught plus by minus by naught equals 0. Now we could tidy this up a bit by remembering that the only real variables here are x and y. We are assuming that a and b and x naught and y naught are constants. Remember, a and b are the components of our normal vector. That's something we're assuming we know. X naught and y naught are the coordinates of our of the point the line passes through. Again, we're assuming we know those values. So I'm going to move all non-variable terms to the other side of the equation. So that's this term and this term. I know a and x naught, I know b and y naught, so there's not really variables there. So that gives me ax plus by on the left-hand side and ax naught plus by naught on the right-hand side. And now what we could do is we could say, oh, well, all of this is a single number. I can take a and multiply by x naught. I could take b and multiply by y naught. And so together that gives me, let's call that number variable d, or constant d. And so I get, or actually let's call it constant c. And so I get ax plus by equals c. So that general form of a line we can derive using this logic. Okay? Just to get a feel for it, let's do an example with actual numbers. Okay? So find the equation of a line passing through the point 2, -1 with normal (3, -5). Okay? So before we do the arithmetic, we could kind of graph it to see what's going on here. So point 2, -1 is right here. I'm going to sketch my normal from that point. So 1, 2, 3 to the right, and then -5 for the y. So that's 1, 2, 3, 4, 5 more down. So 3 to the right, 1, 2, 3, 4, 5 down. Let me make it dotted. Okay, that's our normal vector. 3, -5. Here's our point 2, -1. And so our line is going to be orthogonal to that normal vector. So it should be something like this. Okay, let's find its equation. So we know we should have 3, -5. That's our normal vector. And if we take the dot product of that with any vector parallel to the line, we should get 0 because the normal vector is orthogonal to the line. So if I take some point here, xy, then the vector pointing to from this point to any other point on the line xy, I could express that as end. I want the vector to end up at the point on the line xy minus start. I want to start at the known point on the line 2, -1. So the dot product of the normal vector with the vector pointing from 2, -1 to a point on the line xy. They need to be orthogonal, so their dot product is 0. Okay? I'm going to do the vector arithmetic a little fast. If I subtract these two vectors and then take the dot product with the other one, I get 3 times x minus 2 plus -5 times y minus -1. Okay? And so technically we have the equation of a line right there. But I could go ahead and distribute that 3 here. I could distribute the 5 here. Let's see what we get. 3x, and then 3 times -2 is a constant, -6. -5 times y is -5y. And then -5 times 1 is a constant, that's -5. And so I can move all my non-variable terms to the right, keep my variable terms on the left side. So 3x minus 5y I keep on the left, and I'm going to move the 6 and the 5 to the right. And so I get 3x minus 5y equals 11. That is the equation of this line.